Hey vsauce, Michael here. This point of light in the sky is Earth, as seen from the surface of Mars. And this is Earth as seen from Saturn. Here's an image taken only 45,000 kilometers away, the famous blue marble. But what does Earth really look like? Well, it depends on how you define look. The word look comes from the old Breton word lagud, meaning eye, the human eye. And that's part of the problem. Images like this are based on light humans can see, but we don't see everything. There's a fantastic episode of Radiolab that uses sound to illustrate just how different other creatures' visual spaces are from our own. When we talk about the way something physically looks, we are talking about the visual perception of emitted or reflected electromagnetic radiation, specifically visible light. Light we perceive as red has a longer wavelength than blue or violet. But what if I crank the wavelength even shorter? Does it stop being light? No, it just becomes light you can't see. Ultraviolet, X-rays, gamma rays. Going the other way, you get infrared, microwaves, and finally, radio waves. In principle, the spectrum of possible electromagnetic wavelengths is infinite. But even within the range of wavelengths we observe, the breadth is breathtaking. If the entire practical spectrum of wavelengths was laid out linearly from New York to Los Angeles, the visual portion we see would only be the size of 100 nanometers, small enough to slip through a surgical mask. Point is, when it comes to what there is to see, our eyes miss out on a lot. For instance, take a look at a remote control. Many of these things communicate with light of wavelengths we can't see, but mobile phone cameras can. Try this at home. Push a button on a remote control and you won't see much, but use a mobile phone camera to detect wavelengths you can't see and have them rendered visible. There's a whole lot going on we miss out on. Our night sky is full of frequencies we can't see with our eyes alone, but chromoscope.net allows you to extend your vision. This is the Milky Way as we see it, the visible light it gives off, but slide to see how it would look if our eyes sensed other frequencies. Of course, we are having to represent these other frequencies with visible colors, because even electromagnetic pretend time is bounded by our puny limits. As for Earth, if we only saw infrared frequencies, it might look something like this in our minds. Ultraviolet and extreme ultraviolet vision would return unrecognizable spheres. With X-ray vision, auroras around the poles would shine brightly, and gamma-ray vision would give Earth a bright edge from high-energy electromagnetic radiation hitting the atmosphere at a shallow angle. So, which view is correct? Is there an absolute true appearance of the Earth? We haven't even started yet. Look back at the blue marble. What's with the tyranny of north meaning up? Perhaps it's because we often equate up with better, and many early map makers were from north of the equator. But upside-down maps are equally true, no matter how strange they may seem to us. Funny enough, the famous blue marble itself is a product of north equals up bias. It didn't originally look like this. The crew of Apollo 17 originally took it like this. NASA rotated it to fit our traditional idea of up after the fact. Here's a visual of Earth that comes from the US Naval Observatory's live animation of our planet. You can see exactly what parts are in its shadow at this very moment. Other shadows fall on Earth as well, like the moon's shadow. Last week, Bad Astronomer shared this image. The dark smudge on the left is actually the moon's shadow during a solar eclipse as seen from above Earth. There's another problem with the blue marble. It's flat, and the Earth is three-dimensional. A globe is the best way to represent the Earth, but globes are difficult to carry around, and even when displayed in 2 dimensions, well, you just can't see everything at once. A flat map of the Earth is really convenient, but it requires projecting a globe onto something flat, and a sphere's surface cannot be represented on a plane without distortion. The West Wing famously pointed out the limitations of flat maps. There is no such thing as a perfect flat map of the entire world. Some maps are useful for some things and other maps for other things, but it is really fun to pick on the Mercator projection, mainly because it's so popular, and is even used by Google Maps, mainly because it's so easy to zoom in on. It preserves shape decently well, but suffers when it comes to area. As I've shown before, Africa is huge. Its area is so large, the entire contiguous United States could fit inside of it, along with all of China, India, Japan, and much of Europe. But on the Mercator projection, scale near the poles is pretty wonky, distorted, which means Greenland appears to be as large as Africa, even though in reality it is only 1/14 the size. There's more. Check out Alaska and Brazil on a Mercator projection. They appear almost the same size, but in reality, Brazil is nearly 5 times bigger than Alaska. Areas near the equator are minimized, whereas areas closer to the poles are exaggerated. To have fun with this problem, play the Google Maps Mercator puzzle. The red pieces are countries projected outside of their usual locations. Now, what the heck is this weird shape? Well, let's pull it away from the North Pole where scale is distorted a lot, and oh, it's Australia. You can see how the math behind map projections distort Earth by interacting with them on Jason Davies' brilliant site. Notice how small Greenland appears on the Mercator projection when pulled down to the equator, and how exaggerated it becomes when moved to the edge. To be fair, the Mercator projection is great for navigation. If you want something that is more fair when it comes to area, try the Gall-Peters. Here, land masses are the right relative size, but shape is sacrificed. Everything looks a bit too narrow. Enter the Mulvide. This projection shows equal areas and is a bit more pleasant shape-wise. If you interrupt the Mulvide around the oceans, relative area is preserved and the shape of land masses becomes even more accurate. When it comes to the shortest route between 2 places on the surface of the Earth, mnemonic projections are really cool. Every straight line journey taken on Earth's surface is actually part of a great circle. On Mercator projections, actual straight line paths look curved, but every straight line on a mnemonic projection is also a straight line in real life, the shortest route. If you want a compromise between shape and area, you might try the pleasant Winkle triple, which the National Geographic Society has used for maps it produces since 1998. Or a beautiful butterfly map that can be a ball until it's flattened, say under a pane of glass. The Dymaxion map can unfold to show how nearly connected Earth's land masses are. It's a great way to visualize human migration over time. It's quite impressive how far and wide humans have traveled on Earth, but it remains a bit of a disappointment to realize just how narrow our slice of visual perception really is. But don't feel bad. This brings us to the story of Julian Bayliss. Yes, hello, is this Dr. Julian Bayliss?
Yeah, speaking.
Bayliss told me about how one day, while using Google Earth, he spotted some dark green vegetation. It looked like a rainforest. An expedition was scheduled, and it turned out to be just that, a rainforest we had previously never seen. I asked him more. So what have you found there?
To date, we found about 12 new species, just from Marbu. So we found about 3 snakes, 2 chameleons, a bat, about 4 butterflies, 2 new species of plants. And we've only really just been into the forest edge. So I read a paper the other day, a scientific paper. They estimate that there's maybe 8.5 million species in this world, but we've only actually discovered 1.5 million, or between 1.5 and 2 million. So we've actually only discovered maybe 1/5 of everything that's living on this planet.
Wow, our eyes only see a tiny fraction of what there is to see. But within that tiny fraction, there are still an enormous number of things left to find. So keep searching, keep looking.
And as always, thanks for watching.